I thank all of you for watching my videos. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We will now discuss the solution of a problem that appeared in the CSIR National Eligibility Test held in the month of July 2024. The question is from the section Analysis and it is related to the convergence and divergence of improper integrals. The question is from the part C, which is a multiple select question. There can be more than one answer and it carries 4.75 marks. The question ID is 704066. This question is suitable for the aspirants of JL, DL, TS set, AP set, IIT JAM and GATE. Right. The given question is, consider the improper integrals. We are given two improper integrals. The first one is I is equal to integral pi by 2 to pi of 1 by root of sin x dx. The second one is for a greater than or equal to 0, I suffix a is equal to integral a to infinity 1 by x into under the square root of 1 plus x square with respect to x. We are given four options. Option 1, the integral I is convergent. Option 2, the integral I is not convergent. That means one of them is true. Option 3, the integral I suffix a converges for a is equal to 1 by 2 but not for a is equal to 0. Option 4, the integral I suffix a converges for all a greater than or equal to 0. Let's now discuss the solution of the problem in detail. We first consider the first improper integral I, that is equal to integral pi by 2 to pi of 1 by root of sin x dx. Now, look at the integral. The integrand, it is a finite interval. That means a bounded interval. But the integrand is unbounded at x is equal to pi. In other words, this function is discontinuous at the upper limit x is equal to pi. That is why it is an improper integral of second kind. The reason is the integrand, that is 1 by root of sin x, is unbounded or discontinuous at x is equal to pi. Right. Now, let us consider g of x is equal to 1 by under the square root of pi minus x. X belongs to the interval pi by 2 to pi, open at pi n and closed at pi by 2. Now consider the improper integral, integral pi by 2 to pi g of x dx. Right. Now note that f of x is greater than 0 and g of x is also greater than 0 for all x belongs to pi by 2 to pi. Whenever I say pi by 2 to pi, it is closed at pi by 2 end and open at pi end. Now we are testing the limit comparison. Limit extends to pi minus. That means it is left limit. It is left limit of fx by gx. Limit extends to pi left. Fx 1 by root x to 1 by g of x is root of pi minus x by 1. That is, limit extends to pi left is under the square root of pi minus x by sine x. Now, can the limit go inside the square root? Can it go under the square root? Yes, because it is a continuous function. Which is a continuous function? The square root function is a continuous function. So therefore, it under the square root of limit extends to pi left, pi minus x by sine x. Now you can see limit extends to pi minus. The numerator is 0 and the denominator is 0. It takes 0 by 0 form, which is an indeterminate form. To evaluate it, we use L'Hopital's rule. And that is equal to under the square root of limit extends to pi left. The derivative of the numerator is minus 1. The derivative of the denominator is cos x. Now, under the square root of, take the limits, minus 1 by denominator is also minus 1. That is, we get 1, which is a non-zero finite number. Now recall limit comparison test. By limit comparison test, both the improper integrals converge or both of them diverge together. So we take the integral pi by 2 to pi g of x dx. Right. That is integral pi by 2 to pi gx is 1 by pi minus x root of pi minus x, that I have written as pi minus x to the power of 1 by 2 dx. And it is convergent. Why it is convergent? Because integral a to b 1 by b minus x to the power of p converges if and only if p less than 1. This is a very well known result under improper integrals. So therefore, here the p is 1 by 2. 1 by 2 less than 1, therefore this also converges. Therefore, integral pi by 2 to pi g of x dx converges. Therefore, I, that is integral pi by 2 to pi f of x dx also converges by limit comparison. So, it also converges. Right. So, that means I also converges. Look at our options, and option 1 says the integral I is convergent. Therefore, option 1 is true. We continue the discussion in the next slide. Right. We take the second case, second improper integral. It is for a greater than or equal to 0, I suffix a is integral a to infinity 1 by x multiplied by under the square root of 1 plus x squared dx. Now, how this is improper integral? The interval of the integration is unbounded. And that's the reason why it is a improper integral of first kind. It is of first kind because the interval of the integration is unbounded. Agreed. Now, you can guess g of x from here. So, 1 by x, you take a x square common from the under the square root, that will come out to be x. So you will get 1 by x square. The auxiliary function, so to speak, g of x to be 1 by x square. Now, I of a is integral a to f, integral a to infinity f of x dx, where f of x is 1 by x multiplied by under the square root of 1 plus x square. Consider g of x is equal to 1 by x square. X belongs to the interval a to infinity. It is semi-closed closed at a end. And consider the improper integral a to infinity integral g of x dx. Agreed. You can see now f of x and g of x, both of them are positive for all x belongs to the interval a to infinity. Agreed. Now we go for limit comparison again. Now in this case, limit extends to infinity of f of x by g of x because of this. That is equal to limit extends to infinity of 1 by x under the square root of 1 plus x square. This is fx. Into gx it is reverted x square by 1. Now limit extends to infinity of 1 by x into, take a x square common under the square root, that will come out as x out of the integral, out of the square root, x into x, and under the square root of 1 plus 1 by x square multiplied by x square by 1. Now this is limit extends to infinity of 1 by under the square root of 1 plus 1 by x square. Take the limits, you get 1, which is a non-zero finite number. So you can apply limit comparison test. So we continue in the next slide. So this is what we have done, and we have seen limit extends to infinity fx by gx is 1, which is a non-zero finite number. By limit comparison test, both the improper integrals, that is integral fx dx and integral gx dx, both converge or diverge together. Now we attack the integral a to infinity g of x dx, that is integral a to infinity 1 by x square dx, and that is equal to, after the integration, it is equal to minus 1 by x from a to infinity. And when you evaluate, for the upper limit it is 0, for the lower limit 1 by a, this is plus 1 by a. It exists when a greater than 0. Now in this case, a is greater than or equal to 0. Now 1 by a exists when a greater than 0, does not exist when a is equal to 0. So that means to say integral a to infinity g of x dx is convergent when a is greater than 0, and it is divergent when a is equal to 0. If you take a is equal to 1 by 2, even then integral a to infinity g of x dx converges. So IA, therefore the same situation will be there for I of a. So the I of a is equal to integral a to infinity 1 by x under the square root of 1 plus x square dx is convergent when a is positive, and IA is integral a to infinity 1 by x under the square root of 1 plus x square dx is divergent when a is 0. When a is 0. So suppose we take a is equal to 1 by 2, even then it is convergent. When a is 0, it is divergent. Let's now call on our options. Option 3 says the integral IA converges for a is equal to 1 by 2. Yes, it is convergent for a greater than 0. For all a greater than 0, a is 1 by 2 is greater than 0, so it is convergent. But for a is equal to 0, it is divergent, but not for a is equal to 0. Thus, option 3 is true, and the option 4 is not true because it includes a is equal to 0. When a is 0, IA is divergent. Therefore, option 4 is not true. So thus, option 3 is true. The answer to this question is option 1 and 3. That is the detailed discussion of the solution of the problem from the section analysis, which is related to the concepts of improper integrals. To work out such problems, you must remember the tests of convergence of improper integrals. So concentrate on that and prepare very good notes comprising of all the results of the convergence of improper integrals. I am sure that you have understood the solution of this problem. I thank you for watching my video. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Let's meet in another episode of learning. I wish you all the best. Thank you.